Hello, thank you for joining us today. My name is Kristen St.John, and I'm the head of Stanford Library's Conservation Services. I'm also one of the co-leaders of the Linked Conservation Data Consortium, along with Athanasios Velios, lecturer in documentation at the University of the Arts London. You'll be hearing from him soon. Due to the high interest in this workshop, we decided to open up the lecture portion to all applicants as a webinar. We will also be posting these lectures on our website. For those applicants who are accepted into the second hands-on modeling sessions later today, you will have been sent a second Zoom link to switch to as the lectures are over. We're sorry we could not include everyone in these sessions, but we will communicate with you to see whether a separate workshop can be organized or to explore other ways to work with you. So in this first morning session, I'll discuss our consortium and our work so far. Then Thanasis will give an introduction to linked data and how we're approaching it for conservation documentation. Finally, we'll be joined by Stephen Stead, who will discuss the CIDOC-CRM, the ontology we've been using as the basis of our linked data modeling. That will wrap up today's webinar. Tomorrow, we will continue with a discussion of a pilot project we've had underway for the past year, modeling a group of conservation treatment reports from 4 different institutions. Over the past 2 years, the Linked Conservation Data Consortium has brought together conservators, conservation scientists, and experts in the realm of linked data to explore how to make data from conservation documentation more accessible, distributed, and visible through the use of specific standards, technologies, and protocols. Some of our partners throughout this process are listed on this slide. We have continued to add to the consortium. Please contact us if you'd like to join. Our work has been funded for the past 2 years through UK-US collaborative grants in digital scholarship for cultural institutions from the UK's Arts and Humanities Research Council. And the projects we outlined for those grants have driven our activities so far. These include organizing webinars and in-person workshops back when we were able to do those, producing reports based on our research, working with our professional organizations on policy development, and as I just mentioned, undertaking a pilot to test out the feasibility and utility of modeling conservation records. We have focused on 3 areas: modeling, terminology, and dissemination. In today's workshop, you'll see what we mean by modeling, or the organization of data by identifying relationships between information. Using the CIDOC-CRM, an ontology developed by the International Committee for Documentation of the International Council of Museums, or ICOM. In workshops like this one, we have introduced conservators to the ontology, and we have worked with conservators to identify where the CIDOC-CRM could be adapted to better reflect our data. Members of our consortium participate in the special interest group of the CIDOC-CRM to advocate for these interests. In our terminology work, we investigate how to represent the way we use words in our documentation for use in linked data. Because linked data is, by definition, presenting information in a machine-readable way, much of the way we use terms in conservation is challenging. For example, we use the same words for different things. Brain direction means one thing to an objects conservator working with a wood object, to a book conservator working with paper. Or different words being used for the same item is another issue. An example could be blotter versus blotting paper. Both are fine and acceptable choices in documentation, but they are different. Our work has included how to best align terminology like this, as well as mapping relationships between terms. Our field is not particularly rich in vocabulary sources that are ready to use in linked data, although there are some, including the Getty AAT, that are very fine. We do need more, and we need ones that are more comprehensively reflective of our work. In the area of dissemination, along with reports and updates, our most recent work has been focused on data policy. We have worked with 3 major professional organizations in the UK and the US, IIC, ICON, and AIC, to develop a draft data policy, offering, among other things, guidance in sharing, privacy, and attribution of all types of data generated. This is not limited to linked data. We presented this at IIC Edinburgh last November, and we encourage you all to review the draft policy primer and template on our website. It is now under consideration and review by all 3 organizations' boards. Speaking of our website, it includes recordings of webinars and presentations, as well as reports and further resources. I encourage you to dive into this if you'd like to learn more about the things today that we're talking about. Linked open data as a means to share and enable discovery of information has been developed over many years. Adopting this for conservation documentation is a newer endeavor, and there have been many challenges, and there is still much to work out. While some of what we'll present to you today is well established, such as the CIDOC-CRM ontology, how we apply it to conservation is a work in progress. Today, this workshop is not a course in how to use pivot tables in Excel or other off-the-shelf technology products or solutions. Your engagement, creativity, and analytical skills matter, as does keen consideration of your documentation practice. And on that topic, we are not here to insist everyone start producing the same type of documentation report or use the same type of database. Having the documentation available as structured data or having metadata about your documentation is needed. Your documentation reflects your internal practices. And so, for example, we do not suggest everyone use the same terminology or have the same definition of terms in your data. We also aren't here to tell you how broadly you should share your data. Although I personally hope you'll be interested in sharing it or some level of it, linked data doesn't mean everything is automatically open to everyone. We know considerations for how much data can be shared outside of one's lab are complex. So with that introduction, I hope you find today and tomorrow engaging and fun. And I'm going to ask Athanasios now to share his screen and his presentation. Thank you.
Okay, so I'll start then by repeating what Kristen said earlier about the resources that we have on the website already from the previous meetings. Especially the first webinar was the one that we also described linked data. But also we have a separate introduction to linked data section on the website where various documents exist. So I'm very much approaching this field from a conservator's point of view, as I trained as a conservator, and only later I got more interested in documentation and linked data. Okay, so what is linked data? Well, we could say that linked data is a set of tools and practices to help integration, but not any tools and practices that are specific to the World Wide Web. And you will have recognized the World Wide Web Consortium logo at the top over there. So when we're talking about linked data, we're talking about data that lives on the web. You can, of course, use tools and the same practices to implement linked data in a small system offline, but the whole idea of linked data has been developed because of the World Wide Web. Now, the next question is, of course, what is integration, data integration? And we could say that we have data integration when data from different places are combined. And by combined, I mean, imagine having multiple databases across the world, or maybe multiple databases across an institution in different departments. And you're able to search all of these things as one data set. So integration means that I've got all these separate databases, sources, and they all appear as if they're just one. And an important question is, why do we need data integration? And I think I've got two answers to this question. The first one is that we need to increase the sample from which we are making our conclusions. So imagine if we have an expert on a specific area of conservation, or if we have multiple experts rather on a specific area of conservation across the world. If I wanted to have a sort of a representative understanding of what this area is, I would go and look for information from every single one of these experts. It doesn't really make sense to only look at one place and expect that my conclusions will be accurate and representative. So increasing the sample is one reason why we want to integrate data. Another point is that different experts have also small areas of expertise. So I may be expert in one area, but I want to consult with an expert in another area and bring these things together to produce a global understanding of what I'm talking about. So these are like pieces of a jigsaw puzzle. Some expertise here, some type of data appearing here, other type of data appearing there. I want to bring them together and find out what they tell me when they're brought together. And I've summarized here the benefits, or some of the benefits, for data integration in conservation. This is a slide with a lot of text, so don't worry about reading it. We're going to share the slides later on, and you will have time to go through it in detail. But I'll just focus on the headlines, as it were. So as conservators, we want to understand the technology of objects, how objects are made in order to work on them. By bringing observations from different places, different collections, we're able to improve our understanding. The same applies for materials and techniques for treatment. If somebody has already used a new material or applied a technique in a treatment, then I want to know what their observations were so that I can make reasonable decisions in my work. Imagine if we could identify patterns of damage and correlate that damage to various parameters. Work like that is already being done, but people take a lot of time to collect the data. If we were to share data through linked data, we would be able to provide this information much faster. And then again, we have this idea of correlating environmental control parameters with condition survey results. The fact that I changed my relative humidity 5 or 10 years ago in this storeroom, has it made any difference in the condition survey results that I get today? And things like trends in the work of conservators. Do we work faster? Do people from different countries or different regions or different museums work in a different way? What is the kind of work that conservators do across the world? Estimating the condition of collections at a broader level is very important when it comes to strategy, policy, and of course, funding. So all these questions, perhaps we can answer if we integrate our data across the field. And this is, I'm going to explain now how this could be done. So we have a database, we have a few institutions here, they want to share their observations, their records. So we have, say, a database from Stanford Libraries, and you can see the fields at the top of the slide over there. These are the database fields, yeah? And we have similar fields from another database at the Library of Congress. One would examine these fields, or rather examine the data that goes in these fields, identify the similarities in the kind of data that exist across the two databases, and then draw lines and say, okay, whenever I find this type of data in this field, then bring it jointly with the field from the other database so that they appear as if they're one thing. So this is a bit of a mapping exercise, and across two databases, it's a fairly straightforward thing to do. But you have to imagine that if we add the other three databases now, that exercise becomes a little bit more complex. I have this network of connections that I need to maintain, and no doubt I will discover that a couple of fields from other databases do not exist in mine. So what do? Do I ignore them? Okay, I can ignore them. I ignore some data. That's one way of doing it. Maybe somebody would say, well, why don't you create these fields in your own database as well? In which case, the choices that somebody has made in the British Library affect the database in Stanford. This doesn't sound like a very tidy arrangement of things. Or imagine if I have an established connection between fields across two databases, and then the National Archives decide to change these fields and add slightly different data in there that no longer correspond to my original field, or to delete a field because it's no longer in use. Then all these connections start having problems. It's a very difficult thing to maintain. Even if we manage to do it across one consortium, no one can guarantee that all this work can scale up to another consortium, which still maybe, almost likely, most certainly, we wouldn't be able to talk to each other. So this approach of direct mapping doesn't scale up nicely. Another way of doing it would be to imagine a global structure, a place where every possible field that we will ever need exists. And if every possible field is there, I can easily connect all my fields from one database to that. And everybody can do the same. So we all push our data to this global structure that has space for everything and search that. That would work. And that also would take away the problem of somebody changing something and everybody else having to make changes as well. Because now each institution is responsible for its own database and how that database connects to the global structure. The question is, of course, what is that global structure? What magic box is that? And this is where linked data is giving an answer. When we are considering our data at the global level, we have to forget the local structure we've got. And we have to understand that everyone looking at our data in the global structure does not have the understanding that we have. They don't know what software we're using, what structure the data is, what terminology we're using, what kind of data we're producing. All of these things need to be explained and described in the global structure so that other people can understand our data. So one tool, one technology from linked data that can do that is the resource description framework. And this tells me that every record I've got in my data, or nearly every record I've got in my database, can be described by a simple structure. And that structure is subject connected with a predicate, a property, to the object. What do I describe? What property of that thing and what value does this property take? This is an example here. What I'm saying here is that there is the left board of a book that was bound in Oxford is made of wood. So my first line says that there was a binder that undertook the binding work here and produced a book. The second line says that this binder undertook the work in a place called Oxford. Then the third line tells me that there's a left board, which is part of the book. And then the last line tells me that there's a left board, which is made of wood. Okay, so I can describe my record in these triples. So now I don't need to worry about my local database structure. Yeah? I could have all these records in any database structure I want. Now I have translated all that to a global structure consisting of triples only. The problem is, of course, that, okay, I'm talking about a book here that probably lives in a library. What if there is another book with an identical shelf mark in another library? In the global structure, in the big box, people approaching my data wouldn't know which book I'm talking about. So we're taking advantage at this stage, another technology, very popular, of course, in the World Wide Web, the basis of the World Wide Web, which is using web addresses. Instead of using MS1234, I can say, why don't I use a web address pointing to a page about this book? So if somebody doesn't know what I'm talking about, which book I'm talking about, they can go to that page and find out. I'm solving the global context here. So I can now replace the entries that I had for book in there with that web address. And I can do the same for the left board. This points me to a page that describes what the left board of that book is. Yeah, and you will see now that these web addresses are getting a little bit difficult. I have to type all the time, http:// and so on. And it's the same everywhere. So instead of having to do that all the time, maybe I want to replace it with a shortcut. And I'm choosing MS:. As that's my choice. I'm talking about exactly the same thing. It's just making it easier to type. So don't be confused about that. I'm going to do the same for production as well. So I've got all of these things replaced. Now, in the linked data world, these addresses are called URIs, Uniform Resource Identifiers. and I need one for every single thing that I'm talking about, including, of course, Oxford. You will know that there are many Oxfords in the world. Which one am I talking about? Well, I know which one I'm talking about, but people accessing my data through this global structure will have no idea. So we need to find the right URI for it. So the Getty maintains something that is called the Thesaurus of Geographical Names. And I can go in there, I can search for Oxford, the right Oxford, the Oxford that's in England, as shown over here. And then I can click on the semantic view link. And that gives me the URI for the Oxford that I'm referring to. Yeah, I can take that and put it in my structure over here. And I'm doing the same for wood. The Getty maintains the Art and Architecture Thesaurus. I can search for wood in there, click on the semantic view, and then I get the URI. I can put that in my triple down there as well. And I can reduce these with shortcuts so that I don't have to write all these long addresses all the time. Now, obviously, it is not only the Getty that provides these things. People use different thesauri, different vocabularies, different authority lists according to their domain, what is more convenient for them. So we can use over here references to other things as well. And this is exactly what Kristen referred earlier on. We have produced some guidelines on how to combine and share the vocabularies as part of this project. Okay, so we have done the first column. We have done the last column. We have not done the middle column. We need URIs for the middle column as well. Where do we get these URIs from? These are the properties. These are the connections between left and right side. And the answer is, of course, that we get these connections, these properties from the CIDOC-CRM. Already, Kristen referred to it. I'm not going to say too much about it because Stephen is going to talk about it straight after my presentation. But the CIDOC-CRM is the place where all these properties are being described, maintained, and URIs are available for use. We think that in conservation, the CIDOC-CRM is providing all the properties that we need, or most of the properties that we need. There are still areas that we're not very clear about, like assessing and recording risk. How is that documented? Or things like treatment plans, things that are going to happen in the future. The future. Instructions when we specify how, we still need to explore. Tomorrow we're going to be talking about the importance of these properties. If I have very limited resources, which top 5 properties I would use to implement in my global structure? So we're going to explore that question tomorrow. And of course, there's a lot we learned from previous projects. One of our sister project, Linked Art, led by Robert Sanderson, has already gone through the process of exploring the kind of connections that are needed for museum cataloging. Yeah, so we're looking to learn from that experience. So my final slide is a summary about linked data, and I hope this is clear. So we need identifiers for everything, the URIs, so that we disambiguate every single thing that we're referring to. Then we need to organize these URIs in triples, which is the global database structure that everyone can recognize. That's RDF. And finally, we need to establish the links to resources like thesauri, like the CIDOC-CRM, so that we describe our records, we provide the context, we explain what language we use, what kind of structure we use. So I hope this has been a short but useful introduction to linked data. I'm going to pass on the screen sharing, the microphone to Steve now.
Okay, so welcome to a whistle-stop tour of the CIDOC conceptual reference model. Just to give you some ideas about the types of things that you might want to record and what it looks like. So first of all, I'm going to lead you through the design fundamentals of the CRM, and then very quickly list the core functionality that's supported. And then we're going to have a look at some of the classes and properties that make up the CRM, and the extension that's called CRM Sci, because that has a lot of things which are very relevant in the world of conservation. So that's the plan. So the first bit is this design fundamentals. So what's an ontology? We talk about the CIDOC-CRM being an ontology. So it's a formalized knowledge that gives us an indication of the possible states of affair that might exist in a particular domain of interest. And obviously our domain of interest is cultural heritage informatics, cultural heritage databases. So we clearly define a set of concepts and a set of relationships, the properties that join those classes together, those concepts together, so that they can be processed by both machines and people. So we make our labels for the classes and the properties not only machine readable, but also human readable, so that we can look at them and understand their meaning as wetware, as human beings. So what's a class then? So a class is a category of item in the real world which share some common traits. And we define them using a scope note, what those common traits are. And this is generally known as the intention of the class, so the set of all things which make it up. So individual items are instances of this class. Now, the CIDOC-CRM undertakes two sets of ideas, or incorporates two sets of ideas about the way the world works. The first is that we believe in an open world, that it is not possible for us to know every possible instance of every possible class, of all the classes that we've defined. So we're always looking to make our definitions those which define what something is, not what it isn't. And we always expect there to be things that we haven't seen, which we might see in the future. And we also subscribe to the idea that as our pursuit of knowledge goes on, that we will need to extend the classes that we have so that we can describe more specialized areas. And this is what the work that Athanasios was talking about looking for additional properties, additional things which would be useful in the conservation field that are not currently in the CRM because we haven't yet seen them and therefore haven't incorporated them into the definitions of the CRM as yet. Now, in the CRM, for historical reasons, these classes are named starting with the letter E, because we thought they were something else. We thought they were a different naming convention, but we've stuck with them being called E something because it would just be too painful to change. So we thought they were entities, but in fact they're classes. And we can't be bothered to go through everything and change everything from E to C. So a little historical nuance there. And the definition of a class is done by scope note. So we describe exactly what is meant, so that if you're looking at your data, you can go, I wonder if it's one of those, and go and look at a very precise definition which tells you whether what you have is the same as what we intended you to use this class for. So this really helps us make sure that everybody shares the same understanding of what we're talking about. And this is key to this idea of sharing data across the web, so that if I say that something is an E2 temporal entity in the case that I've put up here, you know exactly what I mean, and you will be able to say, oh, well, that matches my thing in my database. So instead of doing database field to database field mapping, what we're going to do is map a field to a set of things within the CRM, so that when we compare two different database structures, we'll be able to see what each other meant without us having to actually get in touch with the person who curates the target database. So we're using the CRM as a way of describing a global intermediary set that everybody can pass their data up into, and thus gain the ability to talk to other people's data sets without having to do the crosswalking that Athanasios described, which becomes incredibly onerous very, very quickly. So the scope note says what it is. There are some examples, typically with references to point you to where the example comes from. We describe it using first order logic as well, which if you're a computer scientist is nice, and if you're anybody else, so what? You don't need to worry about it. And then we describe the properties, the links that go between this class and other classes. Now, each of the properties also has a scope node. So I'm going to talk a little bit about properties now to put us in the mood for understanding how everything comes together. So each class says which properties it has are attached to it, which start from it. And then when we go on to the properties, we can see that the properties are the relationship between the two classes. And again, they're defined by scope note, and they have an intention, a set of instances in the real world, a set of commonalities in the real world that share them. We always talk about the domain and range, that is where they're going from and where they're going to. So they go from one class to another class. Now, which is the domain and which is the range, which is the starting point and which is the ending point, is completely arbitrary. We have some rules to help us with our naming about which way we think we should do things, and I'll explain those on the next slide. But always, when we go from domain to range, we also have the possibility of going back from range to domain. So that each of the properties is bidirectional. Now, in the CRM, we allow properties of properties, and this is something that isn't supported in RDF, and you have to make some design decisions about how you're going to do that if you want to work in an open world. And there are several different ways of doing it, and those are documented on the website, so you can choose which way makes most sense for your implementation. So if we go on to look at how we name the properties, they're a bit easier. They start with the letter P and then a number. They're always all lowercase, whereas the class names have uppercase starts to the words, and they have a bracketed part, which is what happens when you're reading from range to domain. So they'll always have a bracketed part unless they're actually symmetrical, in which case the same phrase applies in either direction. So when you read from domain to range, so from the starting class to the target class, you read the non-bracketed part, and if you're reading it backwards, you read the part that's in brackets. And we have a priority list for which way we decide which is the domain and which is the range. And we always start from the things that we call temporal entities. That's because we regard ourselves as being an event-centric model. We think that things happen linking physical things and immaterial things together. So we decide that that's the priority for us. So if we go on to look at the scope note, which I have here we say what the name of the property, and you can see that it's P11, had participant, so that's if I read it from domain to range, or participated in if I read it from range to domain. And at the top of the scope note, I've defined what is the domain and what is the range. So in this case, the domain is the event and the range is an actor. So an event is something happening in time, and an actor is somebody participating in that event. And now actors can be individuals or groups in the CRM, and we'll look at some definitions like that in a little while when we look at the instances of classes, when we start looking at classes more particularly. The had participant property is a sub-property of another property, P12 occurred in the presence of, and it's a super property of a whole bunch of specializations, like somebody carrying out an activity as opposed to participating in an event, mothers giving birth, groups being dissolved, people joining, other actors to form groups, or leaving a group. And we can also talk about the formations of groups. So these are all different types of participation. We have a quantification, which tells us in theory how a thing's connected. So in this case, it's many to many. So an event can link to many actors, and an actor can be in many events. We represent this in two different nomenclatures, two different ways of saying it. For most people, many to many is the way that they'll be used to it. But again, computer science has a different way of talking about it. So we also represent it in the computer sciencey way, which is 0,n:0,n. If you don't understand that, it doesn't matter. Just read the bit on the left that's not in the brackets. Then we have the scope note, which explains what we mean by participation. And then we had some examples. And again, we have the first order logic so that the computer scientists can understand it more thoroughly for when they're programming. Now, I've mentioned that we have these ideas of hierarchies. That is, the classes and properties are arranged in superclass, subclass relationships for classes, and super property, subproperty relationships for properties. When you move down the structure of the hierarchy of the classes, so we move from a superclass to its subclass, we inherit all the properties of their superclass. So as you go down, the different types of properties that a class can have get richer as we go down the class hierarchy, because we take with us everything that we got from our parent. So all of the properties we had from our parent class are also added to the properties that are explicitly declared for this subclass. So that gives us a nice rich range of things that we can do. Now, property hierarchies for also give us the ability to do super searching. So if we look at something that's very specialized, like a mother giving birth, we can say, well, when I want to talk about participation in an event, I want not just people who participated in an event or performed an activity or gave birth. I want all of them together, and I don't want to have to write a search which means that I have to enunciate every possibility. And this greatly improves our ability to extend, because if we say that each new property we declare is a subproperty of a property which is up in the higher areas of the standard, then when we search using the higher level terms, we get all the subterms, including those new specializations that perhaps we don't know about that are supporting a particular specialized environment like conservation. So that's how the hierarchies work. And here is an example of part of the property hierarchy. So this is the occurred in the presence of, and we looked at a moment ago, this P11 had participant element in the middle here, and you can see that there's a whole raft of things. So if I query for P12 occurred in the presence of, I would get all of the other relationships which are explained by all of these other properties, which are more specialized, which cover particular cases, particular relationships between two classes. So this allows me to query far more easily. And if we look at the hierarchies of the classes, here's the general hierarchy of what we know as CRM base, so the core of the model, the extensions that exist, all bolt onto this to cover different, more specialized areas. And in a little while, I'll introduce you to two of those, CRM Sci, which looks at scientific measurement, and CRM Inf, which looks at supporting, documenting the argumentation that we make as part of our scholarly discourse. So here we can see the class hierarchy. We've started to color code it to make life a little easier, and I have some slides which have been color coded and some slides which haven't, because they're a bit legacy. But this is the new color coding sequence, or one of the prospective color coding sequences that we'll perhaps see more of in the future. Now, another thing that we've built in is this idea of what we call multiple inheritance. So if we look at the single inheritance diagram on the left here, if we had a museum artifact and we divided the museum artifacts into ecclesiastical items that they belong to a particular church, or canisters which have a bottom and a top, a container and a lid. And then we've got a type of object which is a holy bread basket which has a container and lid. If I just say, well, a holy bread basket is a type of ecclesiastical item, it can only inherit from ecclesiastical item, then holy bread baskets get containers and lids, and they belong to a church, and they've got museum number and a collection and a material. But if I want to do a query looking for all things that have containers and lids, I have to know that I need to query the canisters container and lids and the holy bread baskets container and lids. And that means that queries become much more complicated and expensive to write, maintain, and execute. But if I have multiple inheritance, I can say that a holy bread basket is simultaneously an ecclesiastical item, so it gets its belongs to church, museum number, collection, and material, and a canister, so it gets its container and lid relationships from the canister. So now I only need to know about the fact that canisters have container and lids, and then automatically holy bread baskets get container and lids. And here is a holy bread basket that I use for illustration of this principle. Now, another thing that we support in the CRM is an idea of multiple instantiation. That is that an item needs more than one class to describe it. So if you remember the children's game of animal, vegetable, or mineral, where you divided the world up into animal things like cats, vegetables like potatoes, and minerals like metal, an object which is difficult to classify using animal, vegetable, and mineral is something like this picture of a knife, which is a wooden handled iron knife with bone inlay, which is simultaneously animal, vegetable, and mineral. So we need to be able to combine the different classes that we have in the CRM to make up more complex cases, or deal with more complex cases. So for instance, when a museum gains an object, the object becomes part of the museum's permanent collection, we're simultaneously acquiring the rights to the object, we're taking ownership of the object is moving to the museum, and the museum is starting to look after it. We're transferring custody of the object to the museum. Now, there are all sorts of different cases where all three of those things might not happen. So for instance, a museum that has an object loaned to them might have a move and a transfer of custody, but not the acquisition. Or they might have an object which is being given to them and they now own it, but they're not going to look after it. It's going to be looked after by its current owners until they die, in which case it will then be moved to the museum. So we might just have an acquisition without a move and a transfer of custody. So there are all sorts of possible combinations, and rather than clutter the model up with every possible combination of these things, we have very simple constructs, and then we multiply instantiate them to make it easier to build up every complex case that we see in the real world, and perhaps ones that we haven't thought of yet, but we can still bolt these pieces together to give us an overall capability that allows us to represent all of the richness of the real world that we see in our everyday activities of documenting things. So what does the CRM actually support? These are the core functionalities that we've got in place. So we like to identify things by giving them names. So one of the key things that we need to be able to do is to give names to things, appellations. We also observe things and classify them. So we need to say that we've seen something and that we've classified it. We need to take things apart into smaller things. So objects that get taken apart into the top and the legs of a table, for instance. Periods, we can deal with the beginning of the Iron Age and the end of the Iron Age, early Iron Age, late Iron Age, middle Iron Age, early Middle Iron Age and late Middle Iron Age. So we can take periods apart, and we can talk about places. So the room that you're in is part of the building that you're in, which is part of the street that you're in, which is part of the city that you're in. And then one of the core concepts really is this idea that persistent items, that is things that if you look away from them and look back at them, that you know they're the same thing, participate in things that happen, and that gives us our notion of history. And we drive everything from this core concept. All of our recording is driven by this, and that's why we refer to ourselves as being an event-centric model. So we generate history by understanding the set of things that have happened and the entities that have taken part in them. And people are persistent items. You can continue to identify them even if you look away from them momentarily. Excuse me. We have the ability to identify where things are in space and in time. So we talk about periods existing in space-time. So a period is some social, cultural phenomenon bounded in space and time. So the Romans did their stuff in Europe, or during a broad bracket of time, or the Romans in Britain is another period, which is bounded by the shores of the British Isles, or some of them anyway, and the time when the Romans were here. So we can also talk about the location of physical objects in space. We're interested in the influence of things. So we're interested in the influence of objects on activities and activities on objects. So the loss of this nail meant that we lost the horseshoe, which lost the cavalryman, which meant that we lost the battle. So that's an object affecting things, and activities affecting objects. So this this activity of making something made the object, for instance, or using the object to do something. So I typed this lecture on my laptop and caused the laptop to write a copy of it to its hard drive. And then we talk about information objects. So that's books and or the content of books rather, and databases and poems and songs referring to other things. So they could be other immaterial objects, other books and databases, or they could be referring to physical objects in the real world. So we can get information objects referring to anything that we're interested in studying, anything in our domain of interest. We provide for relationships with time. So we have the idea that events take up some period of time. We do not consider that any event takes place instantly. There are no points in time. There are always lumps of time which have some duration. So events start, carry on, and then finish. So they have some kind of duration. We can say that the event was ongoing throughout a period of time, and that it occurred at some time within. So we often refer to these as inner and outer boundaries. So the inner boundaries are between these two red lines in the center, and the outer boundaries are the two orange lines at the extreme edges. So it happened at some time within the gap between the before and the after, and it was ongoing throughout this period of time marked by the two red lines in the center. So that's the core relationship with time. We can then lump all of this together to try and understand how space and time have interacted, or how things have happened in space and time. So here is the story of a chap called Winckelmann, who saw a copy that had been made of an original Greek statue. So a Roman carver, sculptor, made a copy of a Greek original, and this chap Winckelmann saw the copy sometime between his birth and death, and then based on that he wrote a history of art in antiquity. So he created an article. So we have the original Greek statue, we have the Roman copy of it, then we have this chap Winckelmann seeing the Roman copy and using that to form his ideas about how art had been used in antiquity, how people copied it. And across the bottom of the diagram, we can see the different places that these things happened. So the original Greek statue was made in Greece and then copied either in Greece or Italy. But the statue was then kept in the Vatican, which is where Winckelmann saw it. He was born in Stendal, and he wrote his article while living in Dresden, and he eventually died in Trieste. So these are, we can see time and space being mapped out here, and these sequence of events happening which allow us to describe the relationships between the original Greek statue and Winckelmann's article. So if I lay that out in CRM representation, we get something that looks like this. So we have the copy of the original statue, which was produced by some Roman chap, which is occurred in the presence of the original human-made object, which was Hellenistic, which I don't have a picture of, it hasn't survived. And then we have Winckelmann seeing the copy, the E22 on the left, in the Vatican in 1755. And then he created this information object, the history of the art in antiquity, in which he refers to the Laocoon group in 1764. And then eventually Winckelmann dies in 1768 in Trieste. And we also at the bottom now have a reference to Winckelmann's mother, Anna Maria Meyer, and she was present obviously at his birth in 1717 in Stendal. So now we can see those things which I was talking about in the previous slide laid out as a set of CRM class instances of CRM classes and instances of the properties linking those classes together to tell the slightly more complex story that we saw in the previous slide. So let's have a look at some of the CIDOC-CRM now. So this is just the third part of our little discussion about the CIDOC-CRM. How am I doing for time, by the way? Somebody better write something in the text chat saying whether I'm running to time or not. So the core classes then are this idea of temporal entities which drive the model, and temporal entities have relationships with time spans, they occur in places, they have actors who participate in them, remembering actors can be individuals or groups of individuals, and they affect or refer to conceptual objects, so these are immaterial objects, and physical objects, physical things. And there's a nice difference between conceptual objects and physical things. Conceptual objects can never be destroyed. the only thing that can happen is that we can lose the last carrier of them. So if we all forget something, then the conceptual object is lost, but it's not destroyed. Whereas physical things can be destroyed, that is, taken apart to the point where they're no longer of interest to us to record. So that's the red boxes here. In addition, we have two other boxes, these green boxes. So the one on the left is E41 appellations. So this is naming things. So anything in the red boxes can be given a name, and we can also classify them. So we can apply E55 types to them so that we can talk about specializations of the classes. So we can talk about particular types of temporal entity, for instance, like a battle might be a particular type of activity. Now, what's interesting is that E41 appellations and E55 types are both themselves conceptual objects. So we can talk about how the E55 types have come about. So who created them, when they created them, where did they create them, and so on. And we can talk about the evolution of names, because the names themselves are conceptual objects, so that we can talk about how they were created and how they were used, where they were used, and who used them in exactly the same way as we could talk about a song or a set of instructions for how to use a scanning electron microscope. So we get, with this model, the ability to create our typologies and document how we've created them and then how we've used them. And we can look at the history of the names that we use for things as well. So here again is the participation properties, which is one of the core areas that you'll use whenever you're using the CRM in real work. It's one of the core areas that we get to do stuff with. There are other areas of the property hierarchy that are interesting, but particularly participation is one of the core areas that you'll use all the time to relate people, places, and things together. So all of the people participating, all of the objects participating in temporal events will be using part of this hierarchy of properties. So we can now move on to having a look at the temporal entities. These are the most important things because we're an event-centric model. So we have the idea of the temporal entity that is the core of the model, and we break those down into periods, which are social, cultural phenomena bounded in space and time, and condition states. So this castle was in ruins. Then we have events where we can start to have participation, and then activities where we have people doing, and then things that come into existence in the beginning of existence and the end of existence, where things go out of existence. And then there's a whole range of subclasses there, which allow us to deal with particular types of things. So frequently in the world of conservation, we're interested in modifications that have been made to objects and the original production of an object, and also transformations where things have been taken out of existence and made into something else. So for instance, if we take a windmill and turn it into a house, then that's a transformation where we're changing the nature of the object, but we're not changing the material that it's made from. Whereas a modification, in contrast, is where we're changing the material of something, we're not changing its identity. So if I swap the keyboard in my laptop, it's still my laptop, but now it's got a different keyboard. So modification changes the material, but not the identity. Transformation keeps the material, but changes the identity. So those are some key elements that we want to look at. Now, what I've done now is extend this with the CRM Sci extension and CRM Inf to show us the extra things that come in when we add in those extra capabilities. those extra extensions. I've thinned down the pink boxes, which were from the previous diagram, to just show the things which are core to what we're interested in. So here we have some extra stuff around observations, encountering objects as a specific type of observation, and making measurements, including measuring by sampling, which is a type of matter removal. Ooh, there we go. There's your typo. I'd make one. I hit the shift key while I was typing the 1 into S1. So S1 matter removal is a new superclass that goes above part removal, but allows us to start talking about sample taking and the specific processes that are in sample taking, which is obviously interesting in conservation for when we take samples that we're again going to do material testing on. We have, along with observation, we also have other types of argumentation which come in from CRM Inf. So we have belief adoption, where I read an article that somebody else has written and I trust what they say, and I incorporate that into my own beliefs, which is I7. And then we have inference making, which is simultaneously in the CRM Sci extension and the CRM Inf extension. So it's by dint of making sure they both have the same number. So S5 and I5 are the same class. And this allows us to talk about us using evidence to do things, to make decisions about what we believe to be true. And there are particular subclasses of this around data evaluation, simulation, oh look, another typo, great, and categorical hypothesis building. So these are all things that we can use to say what we believe to be true and why we believe it to be, which again is core to the discipline of science. And down at the bottom, we have these extra classes for alteration and physical genesis, which is used extensively in the archaeological record extension CRM Archeo, so that we can start to talk about how things have come into being. And so production, for instance, is a subclass of physical genesis. You can see the CRM Sci adds the ability to do a few things which we wouldn't be able to do, particularly around taking things away as part of a sampling process. So those extra capabilities come in by adding in CRM Sci, which is pretty useful for many of the processes we use in conservation. Now, this is the E70 thing hierarchy. So this is the thing. It used to be called E70 stuff, but apparently that's rather difficult to translate into many other languages. It's a very British word. So it got changed to thing. And so things are, which it can be physical or material. So it's the piece that sits above the physical world and the immaterial world, so that we can talk about both in a single concept, a single class. And it breaks down into the physical world, the material world, which is at the top of the diagram, and the immaterial world, which is at the bottom of the diagram, which deals with things like information objects, linguistic objects, documents, and the typologies are all conceptual objects, so immaterial, as well as appellations, naming things, which we have in the top right here under appellation. So different ways of naming space, for instance, are all parts of different specializations of appellation. So that's the physical world. Now, there are some add-ons to the physical and immaterial world, but particularly the physical world in CRM Sci. So I've added those in here. So we get the ability to deal with samples and bodies of fluids, for instance, which are quite difficult to think of as being objects because they don't have solid boundaries or features where they're delineated areas on an object. We just have, a lake is rather difficult to conceive, to work with as an object or a feature. So we start to introduce some extra things for when we're doing scientific investigation of such areas and creating samples from them. And so there's some extra pieces at the top here in the darker brown, and an extra lump that allows us to deal with physical features and regarding them as a place, so that we can start to talk about segments of matter, the particular bits of matter that have been used as part of sampling, for instance. So that links back to the original material world stuff that we looked at in the previous slide. So how am I doing for time? Because I can talk about this stuff for hours. Got to wrap up. Okay, right. So here's the last little bit for us to deal with today. I've put some more stuff below. When this presentation is passed out, you'll be able to look at those, and all of the slides have notes underneath, so you'll be able to have a look at those in the future. So this is just the actor tree. So we can see an actor can be an individual person or a group, and a person is a biological object, so it relates back to the physical world. So that I'll wrap up there. Thank you very much for your attention.